Okay, so let's talk about movable pivots. A lot of you have probably already seen this type of setup. What I have is a control that I can translate around, and then when I rotate it, this cube will rotate around that pivot. And this can be pretty helpful if you want to, say, pivot a character's pelvis or their hand around a specific point. And the way that this works is pretty simple. What we have is we have the control, and then we have a buffer group underneath that control, and I am multiplying all of the translate values on the control by -1 and plugging them into here so that the child down here, the cube, receives no net transforms, at least in translate. However, once I rotate it, because the buffer group doesn't cancel out the rotations, the cube is rotated around this pivot. So that's pretty neat. But what I'm going to show you is a way that you can have a control translate and rotate without affecting the object, and then have a second control rotate this. So not only could you move the pivot, but you could also orient the pivot before you apply any rotation. So I'll hide this setup and bring up the second one. So this is what the second method looks like. I have a green major control that I can move around, rotate, and you could even scale it, but we're not going to really discuss scale. But then I can take this red one, and I can translate and rotate from that pivot. So I can go up and then orient this control, and then the object behaves almost as if it were parent constrained to that object. So it isn't working in local space, because if it were local space, then this y-axis would be remapped to this y-axis. So I'm actually doing something different than that. So I'll open up the node editor and we can see what's going on. So I will hide these guys because we don't need them in order to understand what's going on. So the first thing that we do is we take the world inverse matrix of control 1. And actually I will bring back that stuff. So I have control 1, which is the green one, that's the parent of the other red one. And we are taking the world inverse matrix from up here and plugging it into a multiply matrix node. So to show you what that would look like, I'm going to take the world inverse matrix node from here, plug it into a decomposed matrix node, and apply it to this locator. So this is what an object would look like if you were just to apply the world inverse matrix. So you can see that it has the opposite translations, and the rotations are a little bit harder to understand, because I can go up, do like 27, set whatever values, but the rotations on here are not just those rotations set to multiplied by -1, because as I talk about in the actual blog post, the translations normally get applied before the rotations, but in the case of this locator, it needs to be able to cancel out those transformations while still going in the order of translate then rotate. So the rotate does not look like the rotations of the object that it's the inverse of times -1. It's more complicated than that. You could do some actual like algebra and find the inverse of a 4x4 matrix, and you might understand more of what's going on mathematically, but I don't think that's necessary as long as you conceptually understand that the world inverse matrix times the world matrix would just create the identity matrix. So they basically cancel each other out. So I'm taking that world inverse matrix and I'm multiplying it by the world matrix down here. And so those two would cancel out. So if I were to remove this middle connection, nothing would happen. We would get no change in the position of the cube ever, because that world matrix is being multiplied by the world inverse matrix, and they've canceled each other out to create no translations or rotations. But what I'm doing in between the world inverse matrix and the world matrix that cancels it out is I am applying the transformations of this object. So basically what we are doing is we are going into the opposite space of this object. Well, actually it goes in the opposite order, because even though we multiply in this direction, this is simulating a hierarchy of going the other way. So basically we're taking the world matrix under locator, so we're moving it here. Then we are multiplying by the rot controls matrix, which would be just having this locator follow along with this red control. And then after that, we are canceling out the world matrix of this green control right here. So we have an object in the world space of this control. We apply whatever transformations are coming from this red control, and then we apply the opposite transformations of this control after that. So it's kind of the hierarchy of green to red to the opposite of green, if that makes sense. If you understand matrices, then that explanation should make some sense. If you don't understand matrices, you're probably better off going back to one of the older blog posts where I explain it a little bit more. But yeah, that is the basics of this technique. You could get some other cool kinds of effects using it. So instead of having a control that you are moving around, you could have this control attached to a curve, so like a spine. So the FK control would change its position along the spine, but it would still rotate the shoulder controls. And this could remain a child of the hip controls. So you could have a sort of variable FK spine without needing to add as many joints as you would on a typical variable IK setup.